Okay, so we are talking about DFA, and we are talking about the how we can build a DFA from a given language. So this is one example we discussed in the last class. Suppose you have a language which is having alternate 0 and 1s. So this is the null string. This is having nothing. So this is also should be accepted. This is 0, this is 1, this is 0 1 1 0 0 1 0. So like this alternate 0 and 1. So we are looking for a DFA, deterministic finite automata, which accept this type of strings, all this type of strings. So in the last class we have seen this is one example where to accept the epsilon, the null string, we need to put the starting state as a final state, because DFA has no epsilon move. It is a deterministic finite automata. So it has no epsilon move. So that is why we need to put the null string, null the starting state as a final state in order to make it, in order to accept this epsilon. So this is the example where it is accepting the all string where 0 and 1 are coming in alternative way. So this has having, so this is one example where f is having, so what is q over here? So this is our a, q sigma delta q0 f. Now what is q? How many state we have? We have q0, q1, q2, q3, q4, q5. We have 6 states. We have 6 states over here, and we have sigma is 0 1 binary string, binary input, and q0 is okay starting state, but if f is here, final state is not singleton here, we have many states as a final state. So here this is one example where final state is not a singleton state. Who are the final state? All the state except the q5, q0, q1, q2, q3, q4. So all the states we are we mark as a accepted state or the final state other than q5, because q5 is the dead state. If we go to q5, I mean that string is not accepted, and then we can write the deltas rules over here. So this is one df one. So this is accepting L of A is nothing but this L. So this is a regular language. So now the question is this unique? I mean whether we can have a better DFA in the sense of number of states is less. So we will see we can have another, we can construct another DFA with 4 states, which is also accepting this language. So let us try with that. So we can have another example where it is accepting this type of string. So q0. So in order to accept the epsilon, we have to make this to be final state. Then we can go to q1 with the move 0, and we can go to q2 with the move 1, and both are accepted. Okay. And from q1, if we see a 1, then it is also accepted, because this is 0 1. But if we see a 0 after reading this, we must go to a state which is referred to be a dead state. So this is 0, because 0 0 is not accepted. So we should not accept the 0 0, it should be alternative. Okay. Now from q2, if we see a 0, so this is so from q2 if we see a 0, we must go here, because this is kind of 1 0, or it may come from here 0 1 0 like this. But if we see a 1, we should go here. So this is, and from here we can, because the deterministic finite automata should have moved for every, so this sigma is, so this is one example. So this is q sigma delta q0 f. So we have our q is So, our Q is these sets Q0, Q1, Q2, Q3, Q3. We have 4 states. We have 4 state. Among these 4 state, we have a final state all except the Q3, which is the date state. If we reach to Q3, those string will never accept it, because those strings are not alternating 0 and 1s. And delta, we can have the rules. So, delta is like this. So, we have 0 and 1 move, and we have Q0, Q1, Q2, Q3. So, delta should be, delta is a function from Q cross sigma to Q. So, it is a deterministic function. So, we should have, this is the input. So, we should have, so for all pair of, this we should have a output. So, this is, so for all Q and for all A, we should be able to define delta. That is the meaning of deterministic. It is deterministic finite automata. Finite because the number of states are finite, and deterministic because it has a move. I mean, for every we are at a state, we have a input, we have a move. Okay. So, this is a function from the Q cross sigma to Q. So, for a given state, we are at some state Q, we have a move A, we should go to some other state or maybe same state, but this is in a deterministic way. So, that we clearly have this function. So, this is from Q0, we can go to if it is 0, we go to Q1, if it is 1, we go to Q2, from Q1, if it is 0, we go to Q3, if it is 1, we go to Q2, and from Q2, if it is 1, we go to if it is 0, we go to Q1, and if it is 1, we go to Q3, and from Q3, will be remain at Q3. But that move is also explicitly given. From Q3 also, if we have a 0 input, we will be at Q3. If we have 1 input, we will be at Q3. So, this is another DFA which is accepting this. So, this is L of A is L, which is accepting this alternate 0 1. So, it is not that we have a unique DFA. I mean, from a given language, we can have many DFA which is accepting this, but the other converse is like if we have a DFA, we have a unique language, but if we have a regular language, then we can have many DFAs which is accepting this. Okay. So, that we can write is, but if we have many DFA, it is desirable to have the DFA which is smaller, like in the terms of number of states. So, let me write this. So, this is, you can say, note or observation. So, first node is, given a DFA, we have a unique language. I mean, given a DFA, we know the language of that, but the given language, given a regular language, L, we know this is regular, then we may have different DFA, we may have A1, A2, maybe more than something, such that L of A1 is L, which is same as L of A2, like this. So, in the last example we have seen we can have 2 DFA, but whichever is desirable, with the fewer number of states are desirable. I mean, we should have a DFA which is having less number of state. So, we should be careful about the epsilon epsilon string, because this is also a sigma star and DFA is not having any epsilon move. So, to accept this we need to put the make the starting state as a accepted state. Okay. So, now we take one more example to construct DFA and then we move to the another finite automata, which is non-deterministic finite automata, which is called NFA. So, let us just quickly take one more example on to build the DFA. So, we want to have a DFA that accept the binary string. So, DFA accepts all binary strings that begin and end with the same symbol, that begin and end with the same symbol, begin and end with the same symbol. So, this is our language. Our language L is like this. So, L is, it should begin and end with the same symbol, like if it is beginning with the symbol A, then x A. So, A is belongs to sigma and x is belongs to sigma star. Okay. So, the epsilon is not belongs to L, because epsilon is, we are not beginning with any symbols. So, here explicitly we are telling that we are beginning, if we are beginning with like this string, if we are beginning with 1 0 0 1 0 whatever may be, but the end symbol should be 1. So, this is our A and this part is our x. So, A x A. So, if we are beginning with 0, then after some time we must end with 0. Okay. Only 0 also, if you are only one string, I mean length of 1, we are beginning with 1 0 and we are ending with 0. 1, we are beginning with 1, ending with 1. So, this is the way. So, all types of this thing. So, this is of this form. So, we want to check whether this language is regular or not. In other words, we need to build a DFA, deterministic finite automata, which is accepting this language. So, let us try that. So, can we have a DFA which can accept that? So, this is again the trial and error method, because so far we do not know this language is regular or not. Okay. So, it is kind of, I mean, if it to be regular we need to have a DFA. So, anyway, later stage we will see the regular expression, then it will give us some light inside that through a way to construct a NFA of automata. Okay. So, let us try that. So, we start with here. So, here we do not need to make this as a final state, because epsilon is not a accepted this null string is not accepted over here. Okay. So, we put a q1. So, if we have 0, if you have 0, then also you are going to final state. If you have 1, then also you are going to final state. So, these two are the final state. Okay. So, now so from here if we are reading a 0. So, if we are having a 0, we can just go here, because 0 0 which is same, and from here if we have a 1, then where we go? Then we must go to the here. Yeah, this is also possible. So, 1. So, that means if we see 0 1, we come here again. If we see a 0, we will only go there, but yeah, but if we see a 1, will come. So, this is again, as I said, this is an trial and error method. So, this is not possible, because if we put a 1 over here, then what is the problem? Problem is, if we see a 0, we go there. If we see a 1, we come here. Then again, if we see a 1, we go there, and this is the final state, but this string is not belongs to L, it has to be 0. So, this is not the way. So, we can have like this. So, we need to take help of another state maybe. We can go to Q3. Now, if we see a 1 over here, we must go to Q3, and if we see a 0 over here, we can, because 0 0 is accepted, fine. Now, from here also, if we see from Q3, so 0 1, and if again if we see a 1 0 over here, we can go here, but if we see a 1, then we must hop over here until we see a 0. Okay. And then we can have Q4 for this node. So, if we see a 1 over here, so this is starting with 1. If we see a 1, we must go here. But if we see a 0 over here, no, for 1 we must hop there, because that is the accepted string. So, for 1 we will be here, but if we see a 0, then we must go there with a hope to get another 1. So, now from here, if we see a 1, we can come here, and if we see a 0 again, then we must go there. Okay. So, this is one example. We can minimize this, I think. I mean, those techniques we will discuss in the later stage, but this is our A. This is our A. We have this may not be unique, because I am sure that we can combine this instead of 2 state, we can have 1 state. Can we try that? Like we can go from 0. So, now if we have from Q2, if we see 0, we can go here, but problem is it is coming alternatively, like here we are 0 input reaching to another 0 input reaching here to the final state. Okay. Anyway, as an exercise you can check whether this is a only one way, I mean this is the only DFA or not, or we can have another DFA with the minimum number of so this is our A. A is again Q sigma delta Q0 F. So, Q is nothing but how many states we have? Q0, Q1, Q2, Q3, Q4. There are 5 states, and sigma is just a alphabet input, binary input 0 1, and the Q0 is the starting state, and here F is we have many, the F is not a singleton set, we have many acceptance state. So, 2 acceptance state we have Q1 and Q2, and what is delta? Delta is the rule. So, for 2 input, and we have Q0, Q1, Q2, Q3, Q4 also we have. So, for Q0, if we see a 0, it is going to Q1, if we see a 1, it is going to Q2, and for Q1, if we see a 0, it is remain at Q1, and if we see a 1, it is going to Q3. there is no dead state over here, it can able to come back here. Again from q 2, if we see a 0, it is going to q 4, if we see a 1, it is remain at q 2, and from q 3, if we see a 0, it is coming to q 1, and if we see a 1, it will be remain at q 3 with a hope that it will reach, it will get a 1 until it until it get a 0, it will be there, because we need to end up with a 0, because we started with a 0. We started with 0, so that means we need to end up with a 0. So, q 3 and from q 4 we have, so if it is 0 will be here, because this branch is started with 1. So, that means it should end up with 1. So, after a few hopping we can, if we get a 1, then we will go to the q 2. So, this is the deterministic rule, like this is the transition rule for this DFA, and so this is our L. So, this is our A. So, L of A is nothing but this. So, this language is regular, this is regular. Okay. So, this is another example where we can have this given a language, we can construct a DFA provided it is a regular. It is not that all language is regular. For example, if you have a language like this, zero to the power n, 1 to the power n. So, like this is basically the number of zeros and number of ones are. So, if we have consecutive 3 zeros, then we should have consecutive 3 ones. So, like this. So, whether this is a regular language or not. So, can we have a DFA? So, if it is a regular, then we should have a DFA to accept this, whose language the DFA. So, can we have a DFA whose language is L? So, this is a DFA. Can you have a DFA A whose language is L? So, answer is no. We cannot, the DFA is not possible to construct to accept, because this is a particular pattern, like we have to memorize the how many zeros we have encountered before going to 1. So, that is the things, but in DFA we have no memory, we cannot use a extra stack or something. So, this will come in the push down automata, that is also a finite state machine, we will discuss there how this can be accepted, but DFA no. Okay. So, now we will move to another finite automata, which is called NFA or non-deterministic finite automata. NFA, this is called non-deterministic finite automata. Or automation. So, earlier it was deterministic and this is non-deterministic. So, there should be a difference like that. Non-deterministic means the rules are it is a non-deterministic is move is not specified, it can be from we have given a state q and given input a. So, the delta of q earlier it was just a p, a fixed state, but here this is not a fixed state, it could go to the set of states. So, that is the difference. So, this move is not deterministic, it is a non-deterministic in the sense of. So, this was case of DFA, it was a fixed state, but here it is not fixed, it can go to many states like P1, it can go to P2, it can go to P 3 like this, it can go to. So, so that is the difference. So, its moves is so P 4 like this. So, delta of q comma a is not unique, it is a set. This is a set like P 1, P 2, P k, and so this is a subset of q. So, it could be any subset of q. Okay. So, that is the difference. So, move is not deterministic. So, it can have it can go to any one of these states. So, these are the possible state it can go. So, that is the idea. So, that is the non-deterministic. Other things are same. So, in the non-deterministic finite automata, we have again the 5 tuple delta q 0 f. This is same. This is the set of all states, all finite states. And this is input alphabet, which is alphabet, and q is the starting state, f is the final states. Delta here is different. Earlier delta was for DFA. For DFA, what was the delta? Delta was a function for q cross sigma to q. It is going to a fixed state, but here it is not going to a fixed state. So, for here delta is q cross sigma to, this is power, I mean the subset, the pow set 2 to the power q we can say, or power set, pow set. Pow set means set of all possible subsets of q. So, like if we take q, if we have A, this is a subset. Anyway, we will discuss this in more details in the next class. Thank you.